We are very pleased today to have as our guest speaker Dr. Eric Masanet. He is the Morris E. Fine Junior Professor in Materials and Manufacturing and also an Associate Professor of Mechanical Engineering and Chemical and Biological Engineering at McCormick School of Engineering and Applied Science at Northwestern University. Dr. Masanet received his Bachelor of Science degree in Mechanical Engineering from the University of Wisconsin at Madison, his master's degree in mechanical engineering from Northwestern University, and his PhD in mechanical engineering from the University of California at Berkeley. He currently leads the Energy and Resource Systems Analysis Laboratory at Northwestern, which develops mathematical models and decision support tools to quantify opportunities for reducing energy and resource use in industrial technology systems. Such models and tools can be used by manufacturers and policymakers to identify technological, behavioral, and policy pathways towards more sustainable products and processes. Please join me in welcoming Dr. Masanet.
Thank you very much, Nancy, for the kind introduction. How is my voice coming through okay? Are you able to hear me well?
Yeah, we are doing good.
Okay. Thank you. It's always a little bit of a question mark starting a presentation like this, talking into a monitor, and not being able to engage with you there in the audience. But thank you very much, everyone, for coming, and thanks to you who have joined online for joining us. And thanks again, Nancy, for the nice introduction. So it's my pleasure to spend a little time with you today to talk about information technology, and in particular, how sustainable is information technology. I'm not going to pretend I can answer that question. It's actually a very complex question, but what I hope to do is discuss some of the trends, some of the challenges we face as a society, and some opportunities we have when thinking about information technology moving forward. A brief bit of background on my research laboratory. So as Nancy mentioned, I lead the Energy and Resource Systems Analysis Lab at Northwestern. Essentially, we're a group of engineers who use models to try to understand the sustainability implications of different technologies, and more importantly, using those models to identify levers we have as engineers to choose better designs, to manufacture using new techniques, and as policymakers who can influence the pathways that these technologies take moving forward. And we typically consider both economic and environmental effects. And environmental effects, as many of you can imagine, are very broad. Energy, resources, pollution, public health, and so forth. So as modelers, we do a lot of research looking at technology systems ranging from manufacturing supply chains. We've worked with government agencies like the California Air Resources Board to use models to help inform how they could design cap and trade. So as modelers, and as a modeler myself, we get the opportunity to try to quantify a lot of these trends and challenges. And so what I hope to do today is give you, well, based on my work to date in this field, in the area of electronics, give you some idea of the major trends and challenges. But I'll also like to give you some example of the research we've done here at Northwestern to try to elucidate at least, what are those impacts and what might we do about them. So let me start, with the title of the talk, the topic I was invited to discuss: how sustainable is information technology? And depending on whom you ask, you may get different answers, and you may get different rationale that is, well, they're all valid, and let's walk through some of those. So how sustainable is information technology? Well, on the one hand, we know that electronics are a major user of energy, and they're growing. Everyone's got a smartphone. Everyone's got a tablet. Everyone's got a laptop. Many of us have desktop computers. And the lines between appliances and consumer products and electronics are increasingly getting blurred. In fact, many of our appliances now have circuit boards. Many of them are smart. Many of them are networked. So just exactly what is information technology? 10 or 15 years ago, that question was a lot easier to answer than it is today. But really what we need to understand is if you look at these two pie charts, what you're seeing are the 1993.
Hey, Eric, I
yeah.
hate to interrupt you,
Sure,
but
please.
your slides aren't coming through.
Oh, they're not coming through.
Yeah, you may have to unpause the screen. Thanks.
How's that? You see it?
Yep.
All right. Well, I'll share these with everyone, or maybe I'll have these recorded, but there's the information on my lab. Here's the big question we're entering now, and here's the first graph. So thank you for pointing that out. I apologize. But what you're seeing here are two side-by-side pie charts. This represents the total energy consumption by U.S. homes as gathered by the U.S. Department of Energy. Their I think every 4-year or 5-year survey of residential electricity and fuel use called REX. What you see here is the left-hand pie chart shows that in 1993, all of U.S. homes used about 10 quadrillion BTUs. That's 10 quads. And that energy use stayed pretty steady, 15, 16 years later through 2009. It rose slightly, but the big difference you see is heating and cooling, which used to dominate home energy use, is now falling with respect to its share of energy use, and the largest growing end use is electronics and appliances. And as I mentioned, what's an electronic device, what's an appliance, those lines are becoming increasingly blurred. So that yellow slice is growing, and even though our overall energy use in homes is, has leveled off, and we're making great strides on reducing home energy use with respect to heating and cooling and insulation, and so we're continuing to add to the energy burden through greater energy use in electronics and smart appliances. And it's not just limited to the electronics in our homes, our smartphones, our laptops, our smart TVs. There's an enormous infrastructure behind all of those electronics that provides the information that we consume. So behind every PC and notebook and smartphone, there's a system of network devices which are sending bits around the earth tied to data centers. And when we look at those data centers, there's been a lot of attention placed on data centers over the last 10 or 15 years. Because of their growing energy use. So this is a nice chart you're seeing here, which was put together by a colleague of mine, a good colleague, Dr. John Kumi, looking at the energy use of worldwide data centers. Going back to 2000, data centers around the world accounted for about 0.5% of all electricity used worldwide. Fast forward to 2010, and we can see, first of all, there's some uncertainties, and I'll talk more about this as I go through my own results. Anytime we build a model, due to lack of data, due to modeling estimates, there are always some uncertainties. But Dr. Kumi put the range of 2010 data center energy use in about the range of 1.1 to 1.5%, or 1.5 to 1.7%. So what does that mean? Well, data center energy use has tripled over a 10-year period. That's maybe not a surprise to anyone who's been following this issue, but it's a growing source of energy use in the world that is basically on the backside of all of the electronics we're using, in front of us, that can't be ignored when we think about the impacts of information technology systems. So let's go over some facts about electronics. Our modern way of life really depends more and more on electronics. 4 billion people in the world. That's an enormous fraction of people in the world compared to other technologies. 4.5 billion people are using cell phones these days. We ship over 300 million PCs every year worldwide. In the U.S., those same data from the U.S. Department of Energy show us that there are about 150 million computers installed in U.S. homes. Half of those are laptops. Laptops are steadily replacing desktops. We have over 400 million rechargeable electronic devices. These are all of our gadgets, our cell phones, our iPods, our iPads, our cameras, and so forth. Nearly 300 million televisions. When I was a kid, there was one television per house. Now, most homes have at least 2, and there are more homes with 3 televisions out there in the U.S. than there are with 1. And all of these devices, granted, they bring us a lot of great, benefits to our lives: entertainment, connectivity, information, knowledge. But they also use a lot of energy, which I'm showing on this next slide. So about 1/3 of home energy use, as we saw in that previous graph from the DOE, is related to electronics. And that share has been growing. So the absolute energy use of electronics has also been growing. And that's about 7 quadrillion BTUs of energy. To put that in perspective, the U.S. uses in total about 100 quads of energy for all uses: transportation, industry, commercial buildings, residential homes. We also have a lot of electronics in office buildings, another 3 quads out there attributable to computers and copiers and so forth. So combined, that's about 1/10 of our energy use in this country we could attribute to electronics. And those are the electronics that are in our homes and offices. We're not counting yet the energy use associated with data centers. And what is that equivalent to? Well, that's equivalent to roughly the annual energy use of all light-duty vehicles, all U.S. passenger cars. So if we think about just how large the energy use is of electronics, think of that. It's about this on the same order as the energy used by all U.S. passenger vehicles. It's also about the same amount of energy that's used by the first 1 billion people in the world's population if we rank them by their energy use. So it's an awful lot of energy. And there's also sort of a backstory to the energy use of these electronics. There's something called vampire power or standby power, which some of you may have heard of. Essentially what this is energy that's used when an electronic device is in standby mode, sometimes when it's charging, or, you know, many of our devices and appliances have clocks and lights and other things on them which really don't relate to the primary function of that product. For example, my stove upstairs has a clock and it has a few glowing lights on it. All of that stuff uses energy. And in the world of energy analysis, we refer to it as vampire power or standby power. A couple of years ago, this is a cartoon from a local environmental group, EcoMyths Alliance. Together with them, we did a radio show sort of putting into context the amount of energy use associated with standby power. And it really is a lot. Going back to this slide, it's about 10% of all the energy use that goes into our electronics these days and appliances is attributable to standby power. That's really power that doesn't go to any beneficial use other than keeping those devices at the ready. So when we hit the remote control, our television goes on and so forth. So that's the energy use of roughly the first 200 million people in the world's population, and just the energy losses, the power losses through vampire power is equivalent to about 20 million light-duty vehicles. That's an awful lot of energy. Now, the story about information technology is not just limited to its energy use. Clearly, all of those electronic devices use a lot of energy, and so does the data center and network infrastructure that's behind it. But if we think about the equipment that's in those data centers, or the guts of your PC, or the circuitry in your television, electronics manufacturing comes with a really large environmental footprint. This study I'm showing you now, the 1.7 kilogram microchip done by Eric Williams, who's now at the Rochester Institute of Technology. This was really one of the first studies to drive home just how great the resource and energy intensity is for manufacturing of processors or other electronic components. So he showed through a life cycle assessment by tracking all of the energy, resource, and materials flows that it takes to make a microchip, that for every 2-gram microchip that comes out of the factory, there's about 1.7 kilograms of material and energy and resource inputs that go into the plant. And you know, some of these are fairly toxic chemicals. There's an awful lot of water use and so forth. So the point is, we're kind of, as humans, I think, really good at visualizing direct impacts. Whether or not we care about them is another question altogether. But we kind of get the sense that, you know, we're using a lot of energy in all of our electronics. But the energy and resources required to manufacture all those electronics is also quite substantial. Luckily, manufacturers are beginning to report on their so-called life cycle footprints. So what you're seeing here is one set of results from Apple, and I provided you with the web link here to Apple's environmental reports. I have to give them great credit because they're one of the few companies that's being somewhat transparent on the footprints of their products. And when I say footprint, I'm referring to the life cycle footprint, meaning to calculate, in this case, the total greenhouse gas footprint of a 15-inch MacBook Pro with a Retina display. We've got to consider the production phase, the use phase, and the end-of-life phase, which could include landfilling or recycling. And if you just look at the slices in that pie chart there at the bottom of the screen, you'll get the sense for a typical laptop, or more specifically, this Apple laptop. The production energy and greenhouse gas emissions account for the lion's share of the footprint of that device over its useful life. The use phase, which is what I've been talking about so far, the direct electricity use, is only about 15%. So think of this multiplier effect when you think of electronics. They use a lot of energy, and then in the systems that manufacture them and provide the resources to those manufacturing plants, there's a very large energy and resource footprint upstream as well, which is fairly hidden to us. And it's not just about greenhouse gas emissions. So I'm providing here a link to one of the few really thorough life cycle assessments that has been done on computer equipment. There are others, but this is one that came out, well, roughly about 10 years ago now, but looked at all impacts across the life cycle, not just energy use or greenhouse gas emissions. What you can see here on the x-axis are some of the other things this study considered. You know, acidifying agents. This contributes to acid rain and sulfurization. Heavy metal pollutants, particulate matter, which leads to poor air quality and human health effects. And on the z-axis going off towards the back, you can see how the different types of computer devices compared. And the point is really that the energy use and the energy and greenhouse footprint of electronics is a really compelling story. But we can't forget that there's also a lot of other resources and impacts associated with the computer and electronics life cycle. So anytime we wait in line for a new iPhone or a new iPad, we have to remember that to manufacture and dispose of those devices, we are basically driving more demand for more resource use, more pollution upstream, and more pollution downstream. And what I'm trying to do in this presentation as well is I'm trying to provide you with links to some really good reports that I've been using over the years or have found in my research get at an issue particularly well. And if we think about the end of life of all those electronic devices, this is kind of a staggering quote from the ILO. Of all the e-waste in developed countries that is sent for recycling, still 80% ends up being shipped, often illegally, to developing countries, where you can see in that picture, often they are recycled and dismantled in not the safest of and healthiest of conditions. And what this chart shows is the sources of e-waste, majorly coming from North America, Western Europe, Australia. Most of those flow to Western Africa or China or India, where there's still a large problem with safe dismantling and disaggregation of those computers so that they can be recycled. So are we improving our recycling in North America? Yes. Having spent a lot of time in California, we had mandatory electronics recycling in that state, which was great. But is there a guarantee that eventually when all those devices get collected and dismantled, that some of those components aren't going to end up, getting recycled in a harmful way? This is a major challenge we have. We're really just starting to address this challenge as a global society. The other thing about recycling is we absolutely should be recycling all of these devices. In fact, I spent 5 years of my life for my PhD dissertation looking into electronics recycling, and it's clearly beneficial from an environmental perspective. We've got to do two things. We first have to make sure that we're recycling all of those electronic devices in a responsible way, not in the way that we're currently doing so, by shipping them to developing countries to be handled in very unsafe manners. The other thing we need to do is we still need to invest heavily in recycling technology. So the graph I'm showing you here is courtesy of a colleague, Christian Hageluken, who is from Umicore, a large metals recycling company based in Europe. They have large smelting and refining operations that are able to extract the metals from waste circuit boards and recycle those. But the recyclers are always go to great lengths to point out that really what makes for an efficient recycling system are the stages that occur prior to metals recovery. So this is a graph he provided looking at e-waste take back in Europe, which by the way has been on the books now for over a decade. We've got to collect from thousands of different points, a lot of devices, bring them to thousands of different dismantlers to break them into different material streams such as plastics or copper or steel. They've got to be pre-processed, and if you look at that equation at the very bottom, based on current recovery fractions, at least as of 2012, you can quickly realize that it's the system that makes for the efficient recovery of materials ultimately from that smelting plant. So currently, of all the e-waste that's out there, 15% of the metals are being recovered because of losses and inefficiencies in the system that precedes that final smelting operation. So can we recover metals? Absolutely. Do we have systems in place that allow us to economically and efficiently recover all of those devices and separate them and recycle all of those materials? Unfortunately, we still don't. So this is a challenge we have to minimize the burden on the environment of the end-of-life stage of electronics. So, but let's talk about the other side of the coin. So one of the things I find fascinating about information technology is absolutely there are major environmental issues we need to address in the life cycle of those devices to hopefully minimize their footprints. But on the other hand, there are quite a few trends that are quite positive when it comes to information technology, which I'll talk about next. So the thing about electronics is there's really no other product out there that improves its efficiency and performance faster. If we look at this chart, which is something called Koomey's Law, so this is an analysis that was led by John Koomey just a few years ago, where they gathered data, time series data, going back to the ENIAC in the 1940s. It was really an impressive study. And they estimated the computational efficiency, the number of computations for each of those types of computers, and the power draw. And what they came up with was something that has since been called Koomey's Law because it very closely resembles Moore's Law. And for those of you who aren't familiar with Moore's Law, it says that the number of transistors will, I think, double every 1.5 years or so. So what Koomey found in this analysis, by plotting out the computations per unit of energy consumption, was that the energy efficiency of these computing devices also doubles roughly every 1.5 years. So it's not that we aren't making tremendous progress on having more efficient computers or more efficient processors. We are. It's amazing just how fast the efficiency of these components has increased. And this extends to other components that comprise a computer, increasingly smart televisions and other devices that use storage. What you see here are data from Dell, John Pfluger at Dell, which plots out the watts, the power draw per terabyte of storage for different types and generations of storage technologies. And here again we see, just going from left to right, going from a traditional 15,000 RPM hard disk drive, moving over on the right to a solid state drive. The power draw per unit of storage has dropped dramatically. And it's due to the innovation that's occurring, how much information we can pack into a given space on a disk or in a memory card, and the efficiency of that is staggering as well. So this is a good part of the story. The devices we're using are getting more and more efficient every year. And what we find is, what you're seeing here are some results of a study we published several years ago, which looked at, well, if we take U.S. data center energy use, look at the red bar at the very top of this graph. That's current as of 2008, so it's not so current anymore, but as of 2008, the U.S. data centers used about 69 billion kilowatt hours per year. That's more than the city of Los Angeles, so a pretty large electricity draw. And through using models and looking at the options available to those data centers, if they were to adopt these more efficient technologies as they're developed, what you see here going from top to bottom are some opportunities. Virtualizing servers, improving server efficiency by buying efficiency-rated servers and so forth, using power scaling. And what we find is we can get, from a technical perspective, down to that green bar at the very bottom, meaning we can cut the energy use of data centers by more than 50 billion kilowatt hours, an enormous reduction just through technology adoption. So this is the upside of the story is technology advances at such a fast pace for information technology. If we're able to leverage that and adopt it, we can continually save massive amounts of energy. Do we do that? Well, I'll show you in a few slides that's also a challenge is how do we transform these systems to make them more efficient, even when we have more efficient electronics appearing on the marketplace. Another nice part of the story is from a client perspective. These are data drawn from Gartner, which were supplied by Kleiner Perkins. They show trends in the shipments of different types of computing devices, and this is a trend that you've all probably seen firsthand. If you go from left to right, green is desktops, blue is notebooks, orange is tablets, and for the first time a couple of years ago, tablet sales overtook all PC sales. So they first overtook desktops, which were losing share to notebooks, and then notebooks are now losing some share to tablets. The upside to that is the energy efficiency story. So I have a table of data here, which is maybe a little bit busy. I apologize. But what I want you to look at is the energy values in 2012. That's the latest year for which we have data. What you're seeing here is the average energy use of each of those devices, kilowatt hours per year. And we can compare a desktop to a laptop. A desktop uses about 3 times the energy on average of a laptop. And so the shift from desktops to laptops came with some nice efficiency gains. And now go down to the bottom of the table and take a look at the tablet. A tablet uses about 12 kilowatt hours a year, give or take. And that's only about 1/5 of the energy use of a laptop. So this shift we're seeing in client-side devices has a nice energy efficiency benefit. For every device that we're using to interact with the internet, gather data, meet our information needs, we're shifting as a society to smaller and smaller thin clients, let's say, that use a lot less energy than their predecessors. And that's an upside. So this technological change really can make a dent in our energy use. And these are data, again, from a study which I showed on the previous slide. Both of these are from a forthcoming study, which was led by Paul Tehan at the University of British Columbia, where we looked at the life cycle greenhouse gas emissions of a wide range of devices that you and I use in our homes, smartphones, tablets, different ways of connecting those through mobile, cell phone systems, Wi-Fi, and so forth, to try to come up with an idea of how these competing trends may play out. On the one hand, we're shifting to smaller devices, and our devices are getting more efficient. On the other hand, we're using those devices more and more to consume ever more content. And so what our preliminary findings are showing is if you look at 2012, which is the top box showing 7 different results in bar graphs for the 7 different devices and systems we considered, the energy use is shifting only very slightly away from desktop PCs and more towards smartphones and tablets. The television is really driving a lot of our consumer electronic energy use. And I'll talk a little bit about some opportunities there. Even with the shift away from, let's say, using DVDs and moving more towards online streaming for content or getting our shows over the air, televisions still represent an enormous opportunity for us to save energy. And what we found is in our analysis, looking at trends of future consumption and general efficiency trends, we're sort of treading water. We may not rapidly increase greenhouse gas emissions due to increased use of all those devices, but we're not likely to either reduce the emissions through greater device efficiency. So on the one hand, device efficiency gets us some nice benefits. On the other hand, we tend to consume more and more media every year, and it's sort of one step forward and one step back. And this is what our analyses, based on the most recent data, are showing us. Now, we do have some opportunities for, in this case in particular, for television, but also a lot of other electronics. So this is also part of the good side of the story. So as a society, and particularly in Europe and in Japan and in California, some of the regions of the world that have been leaders with respect to driving energy efficiency, we have a lot of attention placed on electronics. So for example, just a few years ago, California decided to place an energy efficiency standard on flat panel televisions. They've been doing this for years. They put standards on refrigerators and washers and dryers and so forth, and saved a lot of energy in the state. These data are from Art Rosenfeld, a former California Energy Commissioner and a former colleague when I was back at LBNL, that kind of sums up how these standards really make a difference. So the red line shows the energy consumption of TVs. So for a long time, going back to the 70s, and this is in California, the energy use of televisions was mostly flat. I mean, most homes had one television, maybe two, and they were all, you know, cathode ray tube televisions, which were energy hogs. But in the late 1990s, with the shift towards flat panels, televisions got cheaper, televisions got more ubiquitous, and they started getting larger. So that red line was California's forecast for where the energy consumption of TVs would go in the absence of some sort of policy intervention. And so they came up with this appliance efficiency program focused on televisions, which would shift that curve down to the green line. And that's the benefit we get out of greater attention from a policy-making perspective on electronics, is we can impose some strict standards that prevent maybe some of these unintended or undesirable consequences associated with, you know, cheaper electronics, more ready access to electronics. And the way they did it was this graph. The engineers always appreciate a graph like this, as I do. It shows the way the standards work. So on the y-axis, we've got the on-mode power consumption. On the x-axis, we've got the size of the television that were considered under this standard. And you can see for different sizes listed up on top with these gray bars, 25 inches, 32 inches, and so forth. Those are the diagonal dimensions of the screen. They could take measurements of all the different televisions from different manufacturers and plot them out. And you see a wide spread in those data. And what it says to, you know, an analyst or a policymaker is that there's a large spread, but that the bottom end of the range is probably something that's practical and feasible if it exists on the market already. So the Tier 1 standards pushed really only, let's say, the highest energy users among those television sets, with more severe effects looking at the large screens. And then the Tier 2 standards, which went into effect later, really pushed the market much harder. You can see that if you're on that 42-inch bar, you know, the Tier 1 standards really only affected a few models. But after the Tier 2 standards went into effect, it pushed the performance of that size class down to the best in class. And so there's more of this happening around the world too, and this is a good sign for sustainability. And the Energy Star program has been doing this for a long time, and this has been very successful. What this graph shows is by placing efficiency standards and labels on appliances, Energy Star, our federal program for energy efficiency labels, has saved a lot of carbon across a lot of different areas. And so these approaches do work. I'd like to give you some example now of some work we're doing to try to understand opportunities related to taking advantage of more efficient technologies. So a few years ago, my research group, in partnership with Lawrence Berkeley National Lab, were approached by Google. And Google wanted to know just how much energy could be saved through cloud computing. So clearly Google has an interest in this because they're a cloud service provider, and they know just from running their own data centers that a cloud-based data center is much more efficient than a standard, you know, closet data center that you know, every organization may have. And so we built a model which asked this question: if we could get more computing done in a cloud-based environment as opposed to maybe in the server closet down the hall from your office, how much energy savings would be out there? And not just for Google, but for Amazon, for any cloud provider. In fact, you don't need Google or Amazon to have a cloud data center. If you're a large enough organization, you can have what's known as a private cloud, which means that you just have shared computing resources that are secure and internal, but they're used in a maximally efficient way. So we developed a model for them. The model is actually online if anyone is ever interested in using it. It's called the CLEAR model. And we took a life cycle perspective. We wanted to know if we were to shift from a lot of very small, potentially inefficient data centers in the US to just a few really efficient data centers. And we considered a life cycle perspective, not just how much energy is used by the servers themselves, but also how much equipment would have to be manufactured. Would the energy use patterns change? Would there be more networking energy required if suddenly you had to be getting data from a far-off data center versus right down the hall and so forth? And as I mentioned, the model's available, clearmodel.lbl.gov. And so what we did was we first decided to take a look at, well, what's the market for this? So anytime we want to understand, is there a transformational opportunity in the information technology space, we want to understand the market. And so for business software, I should define that for you. We looked at email, productivity software, and a sales management software. And everyone has email, right? So there are millions and millions and millions of users of this software. And these are mostly run, well, email is largely hosted in smaller rooms in many businesses, which tend to be less efficient than a big, massive scale cloud center. Productivity software is mostly run locally. It could be run over the cloud. And this human resources management software came in. And if we look at the way these, in these charts I just brought up, how it's distributed, most of the email is hosted locally. Most of productivity software, those applications are hosted locally and so forth. So if we could shift those local computations to a more of a cloud-based model, how much would we save as a society? And so the results are pretty staggering, actually. When we consider just how inefficient small local data centers are, if you look at the pie charts on the right-hand side of this graph, we estimated these are rough estimates, of course, somewhere in the neighborhood of 4.9 million servers out there that are hosting these various types of software in all the data centers that exist in the United States. And if all of those computations and services were shifted to massively efficient sort of cloud-type data centers, you can take a look at the size of that small pie and see just how many servers are eliminated when you try to get the maximum efficiency out of every single server that's installed, and you use that server to serve businesses regardless of who they are, basically. It's a massive reduction. And what it looks like is a shift from local inefficient data centers to centralized super efficient data centers would save roughly the electricity use of Los Angeles every year. It could reduce the footprint, the life cycle footprint of those applications by about 85%. So massive savings, and most of the savings were driven, as you can see in this chart, by eliminating a lot of energy waste at data centers. A little bit more energy is required for network transmission, not much. Large savings. So this is one opportunity we have as a society, and I will say for due diligence that anytime we do an analysis like this, we build a model, we populate it with assumptions, which are based on data we gather or we pull from the literature, and there are certainly a lot of uncertainties. So I would encourage you, anytime you see results, just like I showed you, to take a look at the studies and to try to understand what the assumptions are and where the data came from. And despite our funding source being Google, they didn't provide us with any data, which would have been great if they had, but they wanted us to maintain full independence. And like a lot of other companies, they're pretty secretive about what their operations look like. But access to data to even understand what the opportunities are and what the current footprint is another major challenge that I'm going to talk about in a few slides. So that's one example. Now on the flip side, cloud computing is something that really is an ideal end state for us. So ideally, if you have a data center, you want your servers to be maxed out in terms of their workload. because they're sort of like a car. Most of the energy use in your car is to move all the steel and the aluminum, the car itself, as opposed to moving you. The more people you put in that car, the greater the efficiency is per person moved, essentially. And it's true for a server. If you can share servers like we can in cloud data centers, the computations are always high, and what it means is the watts or the kilowatt hours per computation are low. Now, that's an ideal end state. I'm going to show you some results that we just recently generated for the state of New York, where they were interested in looking at the total footprint of their data centers and by how much that footprint could be reduced over time through greater efficiency. So what you're seeing here is our best guess at the distribution of data centers in New York State. In total, we think they use around 7 to 8 million megawatt hours per year. Pretty significant energy load. And what I'm showing you now is a forecast of where energy use in New York State data centers could go if they were to adopt the best available technology over the next 6 years. This means every data center would shift to the most efficient servers, they'd get the most efficient cooling equipment installed, they'd run their operations very efficiently. And this is in light of 20% demand growth per year. You remember I mentioned that we're consuming more and more media every year. This affects data centers. They're required to do more and more work every year. So even in light of 20% growth in demand for computational services in New York State, if those data centers were to adopt the best technologies, as a server burns out, replace it with the most efficient one and virtualize that server. We could see that the data center footprint, energy footprint in New York State would drop by about 40%, all the while meeting, an enormous, demand growth scenario. Will this happen? Unfortunately, it's not very likely. This is what's likely to happen. Instead of reducing energy use by 40%, the state is likely to increase its data center energy use by 50%. Because of that problem I mentioned earlier, that data centers typically are run by local companies and local places in very inefficient ways. Companies don't like to share servers and cloud-based data centers. And so the difference between where we could go, where the technology would allow us to go if we adopted best practices, and where we'll likely go because we have a lot of institutional barriers to adopting best practices, that difference is large. It basically amounts for 100% of that initial energy use in 2014. So studies like this give us some idea of what we can do as a society and where the opportunities are for going down a different path. So for data centers in New York and data centers elsewhere, moving to more shared resource models, adopting the latest, most efficient technology is not necessarily what they are driven to do presently, but if they can do that, they can save an awful lot of energy, as you see here. Okay, I'd like to move on to another sort of upside, a big upside of information technology. Why am I showing you a graph on water use? Well, because I'd like to talk about a smart application of information technology that affects water use as one example. But what you can see here, these are the latest data from, well, I think some new data just came out from the USGS. As of a few months ago, these were the latest data on water use in the United States. And really what you need to take away from this graph are two things. The #1 user of water is for electric power, meaning the cooling of thermoelectric power plants. The second largest use is irrigation. And we can see right here, California, the largest user of water by far, primarily due to all of the agriculture in California. And as we all know, they're going through a very difficult period with the drought. And the economic and environmental impacts of that are going to be quite large. Now, when we talk about how sustainable information technology is, we tend to focus on all those things that I focused on so far in this presentation. The energy use, the environmental footprint of the devices themselves. Now, what we miss out on when we take that perspective is the so-called enabling effect of information technology, which is quite substantial. So think about this example here. So this is something that is basically what you're seeing here is a schematic of an intelligent irrigation system. So presently we may irrigate fields with large sprinklers that we put out when we think the fields need water or they're on some kind of automatic schedule. Imagine if we could provide just enough water to those crops in a way at just the right time, meaning we don't water before a big storm comes in, or we don't water until the soil moisture content dictates that we need to, and the forecast shows that there's not likely to be any rain anytime soon. Well, we can actually do that through systems like this, which require a lot of devices and components. So here we see we've got smart components like an irrigation controller, which actually controls the flow of water. We've got sensors out there. Those sensors are networked. So all of that information on soil moisture and so forth is going to a data station, which basically gets crunched through some algorithms in a computer, which is responsible for controlling the irrigation. There are crop models. How much water do individual crops need? Those sorts of things are taken into consideration. The computer can be networked with a remote server, which could use a weather model to help add an element of probability, so that you don't water the field if there's a certain chance that it's going to rain and so forth. So imagine now the decision-making capability a farmer may have with these smart systems, being able to monitor, communicate, analyze, predict in real time. We could get much more smart about irrigation and perhaps reduce the irrigation intensity for the same crop yield dramatically. These are things we couldn't do 10 or 15 or 20 years ago. And so the enabling effect of information technology is something that has to be considered when we think about sustainability. And in fact, there are so many applications of information technology for environmental benefit, it's impossible to keep track of them all. A few years ago, I guest edited a special issue of a journal, which I'll show you next, where we tried to gather case studies of this so-called enabling effect. And we got some great ones. Smart meters enable anytime, anywhere access to energy use information in the home, and it allows you to control, understand your energy use, make changes, and so forth. Caterpillar, a local company, they use real-time analytics coupled with satellite data, so that grader will be taking out just as much dirt as it needs to and optimizing its driving path so that it doesn't go over the same spot twice. You can't do that. I mean, maybe a very skilled operator could do that, but with data analytics and communications and ubiquitous computing, essentially, that grader or that tractor can optimize its operations in real time. There's some really powerful, compelling examples. I'll show you one on dematerialization. By moving away from printed newspapers or compact discs or DVDs, will we save energy? So you'll probably hear a lot more about the enabling effect of information technology, just because there's such great potential there for energy and resource savings. This is the special issue I mentioned. It's now a few years old. It came out, I think, in 2010, but the sponsor of it wanted to make it freely available. So if you just go to the slides later or Google this title, you'll see about a dozen articles and case studies, at least as of a few years ago, on really interesting applications of information technology to solve environmental problems and to reduce resource and energy intensity in the economy. One in particular is a meta-analysis done by an economist, Skip Leitner, who was formerly at the EPA, most recently at the ACEEE. What he does is he's an economist, so he looks at net effects over time in the economy. And what he was able to show, or at least what he estimated, was that by having semiconductors in our economy, we've delivered massive energy savings already. And if we continue to deploy those semiconductor technologies, we can get even greater efficiency savings through things like building controls or smart systems and so forth. So the way to interpret this graph is the purple line there is essentially, as of the time of this study, the Department of Energy's best guess at where energy use was going. So Skip through some modeling approaches, estimated that we could follow that green line if we were able to tap into all the productivity benefits we get out of semiconductors and computing equipment in our economy. And it's massive savings. You can see just how far that line was bent down. So teasing out this enabling effect, though, is very difficult, and there aren't a lot of researchers, frankly, who are looking into it. I want to make sure I'm okay on time now. So let me go back here. Sorry. I want to give you a quick example before I turn it over to questions. So I'd like to close with this idea of, okay, how sustainable is information technology? We really need to consider the net effects. So clearly there are impacts associated with the technologies themselves, but when we apply them, we can save a lot of energy, a lot of resources in the economy, and how sustainable they are really depends on the net effects. Are the benefits greater than the impacts? So this is a very difficult thing to do. And the reason is we've got many different IT devices, and their uses are very different. And we need to have information on how those devices are used and how they're made. It's great that Apple is putting out carbon footprints of its products, but we don't have data on the materials and the manufacturing locations and so forth for their products or, frankly, any other electronic products. The data are very scarce. We don't have many data on just how these devices are used, for how long, to what purpose. We don't really have good ways of predicting how people are going to use those technologies. You know, Uber and so forth. That's in our, or Airbnb. Those are two disruptive technologies based on information that maybe change the energy footprint of our transportation sector or the energy footprint of the hospitality sector. To what extent are those being used, and for what? What's offset? I'll show you one example of an attempt we made to try to understand if we move to streaming video, what's the effect on the physical systems that we're replacing? All of these characteristics need to be taken into account over time, over space, and frankly, we don't have the data to do it. The data we have, as you maybe even sort of gathered from the data I've been showing you, come from different years and different sources, using different techniques. So there's great disparity across these data sets. Dealing with how fast technologies change over time, that's an issue for us. And there really is kind of a lack of community, a research community, that coordinates on how these models should be developed and shares information from models and, frankly, shares data. So what really matters, I'm going to skip ahead to this last case study. I'll show you one example of how we tried to tease out, I and some colleagues tried to tease out the net effect for streaming video. So on the one hand, when we move to streaming video, we are using more electronics. We are, drawing into the fold data centers and network systems and so forth. What you're seeing here is our best guess at the number of viewing hours of rented movies in 2011. Why 2011? A problem we have in our field is there's always a data lag. So we're analyzing systems, getting data 3, 4, 5 years later, and by the time we're able to get the data, the technologies have changed. So take this with a grain of salt. But what you see here is, as of 2011, most videos, at least we estimated, were still being rented through Redbox or Netflix, even sending you through the mail, versus streaming. And I suspect the situation has changed. And we could look at the existing systems. So if you watch a DVD, that DVD has to be manufactured and shipped. You've got to get it at a store. It's got to be delivered to you and so forth. And there are different ways you can watch it. You can watch it from a DVD player, a Nintendo box, a computer, and so forth. We have to compare that to the streaming system. So the data centers, all the equipment, getting those data to you. How do they get there? Wi-Fi, DSL, and so forth. And what we were able to do is do a life cycle assessment to try to compare these two options and to see, are we saving energy and resources as a society by moving away from physical DVDs and to streaming digital video. So the results you see here compare 5 different scenarios. The left-hand side shows energy per viewing hour, right-hand side shows CO2 per hour, and what you'll notice is really the trade-off we get with streaming is we get more efficient on the end-use client side. The reason is DVD players, they are not so efficient. And when we have streaming video, we start bringing in smaller clients like tablets and smartphones and so forth. So the way we're viewing is changing. We also are eliminating a lot of travel, a lot of transportation, which has a high energy and carbon footprint. That's essentially the net change we're dealing with. We add more energy in data transmission and so forth and hosting, but we save energy by not having to ship things around the economy and because we can use thinner clients. And so what we found was, is this moving us in the right direction? Well, what you're seeing here is two scenarios. The first is in 2011, we weren't streaming as much as we are now. We were mostly watching DVDs. If we add those two up, we get the total. If we were to move everything to 100% streaming, we would actually save energy compared to watching everything on DVDs, but only a little bit amount of energy. And frankly, in the world of modeling, that difference isn't even that significant. So is it moving us in the right direction? We think so, but there are also some break-even points. So in any of these analyses, the more we consume, the higher the footprint goes for the digital streaming side. So for example, you can probably imagine when you have a DVD, you know, you're going to watch it, you're going to buy a DVD, it's going to be shipped to you, you're going to watch it a few times. But the fact that you have that DVD doesn't necessarily mean you're going to watch it more. With streaming, now that we can get streaming video anytime, anywhere for a reasonably cheap price, you know, it means that we've got to deal with the so-called rebound effect, in that now that we can watch more video and it's so convenient to us, will we? If we do, what will probably happen, at least our model is showing, is that we're going to reach break-even points, where when we start consuming more streaming video, we're going to probably start using more energy as a society than we currently were using under the old DVD scenario. So on the one hand, is it more efficient than DVDs from an environmental perspective? We think so. On the other hand, we're likely to consume more, and what that may do is drive up the footprint of viewing overall. So again, it's this tension between impacts and benefits, and how do they shake out over time. So I wanted to close with that example and open it up to some questions. I know I covered a lot of ground, but what I wanted you to take away was, if you think about the sustainability of IT, clearly we can't ignore the direct impacts of making them, using them, and disposing of them, and those are significant by any standard. We also can't ignore the enabling effect. So what do we get out of having that digital service? Does it offset some other service that was less efficient? Or could those devices be applied to directly save energy and resources? Those examples are, you know, they're abounding out there. We've got many more appearing every day. And the only way we can understand how sustainable IT is to take more of a global systems perspective and think about, is it bringing us along a pathway that's going to enable resource and environmental savings in the long term. And I think we have examples of that with respect to that irrigation controller. Absolutely, that's something like that should surely save energy and resources, and probably far greater than the impacts associated with running and manufacturing all that equipment. But when it comes to things like streaming video or music, yes, it does dematerialize our society, but it also means we may consume more, and the implications of that aren't clear. So with that, I'll turn it over for questions, and I thank you for your attention.
Okay, thank you very much, Eric. Very interesting presentation. We'll open it up to questions first here in our audience, and then we do have some online. So is there a question here? Okay, we'll go to the online question.
Eric, this one was from Sandra. Does the data comparing the energy use of desktops, laptops, etc. include the energy used in their manufacturing?
So I showed a table. So the table I showed did not include the energy use associated with their manufacture. It was just the operational energy use. However, in the study from which those data came, yes, we did also consider the energy use of the manufacturing of the desktop, the laptop, and the smartphone. To give you an idea, though, of how energy use, direct energy use, meaning the power to run a computer, compares to the energy use or power required to manufacture it, this Apple graphic, if I can get all the way back to it, it gives you an idea of just, you know, the typical share of production. So different life cycle assessments of computers will give different results, and it depends on the model, the company, and so forth. But in general, about half of the energy use and greenhouse gas emissions associated with a computer will be associated with its manufacture, and about half will be associated with its use. In this case, for this Apple, that ratio is higher. There's more associated with production than use. We didn't in that particular table, but in the study we do, and it's important anytime we think of the energy use of these devices to include the use phase, but also manufacturing and end of life, because there are energy implications there too.
The next question is from John. Recycling, is there an economically realistic pathway that can get a larger fraction of scrap electronics to the smelters?
Yeah, that's a great question. Well, it's a matter of perspective, let's say, of what's economical. So there are models. So, for example, in Europe, manufacturers pay into a system which is supposed to pay for the end-of-life processing, making sure it gets back, a computer gets back, making sure it's handled properly, and so forth. And there are some places in the world that are doing so, in an economical fashion, meaning there's enough money in the system to pay for it. If it were market-based, it's doubtful that we would be able to recycle much of the materials in computers. So the precious metals in computers, gold, platinum, and so forth, the quantities in today's computers are much smaller than they used to be. So 15, 20 years ago, recycling was a net positive, let's say, undertaking for a lot of electronics recyclers because of the metals value, essentially. Now the precious metals content is much lower, and it's tough to make money by recycling. You can't really purchase buy scrap and recycle it profitably. The way the systems work is we pay into it or the manufacturer pays into it in order to make the system economical. The fact that a lot of e-waste is still flowing overseas means that there's an economic disincentive still to responsible handling. Somewhere in that chain, dealers or middlemen are basically making a quick buck and shipping the e-waste overseas. So I think there is a pathway, but I think it's going to have to be a policy pathway where we have greater subsidies, frankly, for electronics recycling in the short term, but then greater investment in R&D for better, more economical and efficient recycling technologies so that we can get the materials out in a more efficient and cost-effective way. The other part of the problem is we have just a chronic issue with consumers, you and me, bringing our computers back. Most of us have an old computer or an old device in a drawer or in the basement or in the garage for a few reasons. Inherently, we know we shouldn't throw them in the trash. That's a good thing. But people are kind of loath to throw them away until they're absolutely sure they'll never use them again. So we also have a supply problem where we're not essentially getting every device we could back into the collection system, which hurts its economics too. So we need to overcome that as well. Get people to recycle their devices in a prompt way rather than stockpiling them.
This one's from Craig. What incentives do you foresee or recommend to guide us down the clean path as opposed to the reference case for the data centers?
Yeah, so data centers are a tough one. So data centers are, they're run by private businesses, and as we all know, and the biggest driver for them is what we call uptime. Meaning, if you run a data center, you'll do whatever you need to make sure you never have a split second of downtime, because if you do, it can make or break your business. And so what that means is you design your data center and your equipment to be really reliable, which you should, and to have the server specs that you should, and you don't necessarily worry about energy efficient servers because it's not on your radar screen. You design in a lot of buffers, a lot of redundancy to make sure that you don't have downtime. And so there are data centers who have figured that out. Google's a great one. Facebook is another company that does a really great job at this. They've committed for a long time to trying to maximize the efficiency of their data centers, sure, from an environmental perspective, but also because it makes a lot of business sense for them. But they have, procedures that are that are tough to replicate for, let's say, the mom and pop data centers. They custom design a lot of their servers. They have really strict layouts. Every aspect of their data centers optimized because that's their business. If you think about most of the other players that have data centers, U of I's got data centers, Northwestern has them. We've got great IT people, but those data centers aren't our primary business focus. And if that's the case, it's difficult to get people to pay attention to efficiency, to elevate it to the same stature as reliability, availability, low cost operations up front, so you get the cheapest equipment you can to do the job, that kind of thing. So changing the pathway for let's say lower energy data centers from a technological perspective is pretty clear. We have the technologies and we have data centers that are doing a really good job on energy efficiency, but they're in the minority because most data centers don't have the same business model and don't have the ability, the know-how, or even the business, let's say drivers to become efficient. So changing us to that lower pathway for data centers is going to require a lot of education, a lot of investment, a lot of subsidies, and overcoming a lot of institutional inertia. Frankly, the technological challenge is more or less solved. Not perfectly solved, but we can always get better technologies, but we're not using what we have.
Okay, well, thank you very much, Eric. I think that'll bring this webinar to a close. If anyone has other questions, I'm sure they can email Eric and ask him that.
Absolutely.
And we'll hope to see or have you online, those viewing today, for our series when it starts up again in the fall. So thank you very much again, Eric.
Thank you.
Bye-bye.